The central principle, geodesic straight line, is the 2.1 expanse ratio designed Rodney-Kawecki model, which governs cosmic motion. It creates a dominant propagation pressure, effectively C2 in conceptual terms. This pressure establishes planar alignment of celestial systems, e.g., solar systems, galaxies. It maintains orbital stability without requiring additional constructs such as dark matter. Under this interpretation, the universe behaves like a high-pressure conveyor system, not a deformable surface. Celestial bodies move along geodesic channels, paths of balanced propagation pressure. 5. Orbital stability and energy. By removing the gravity well concept, several implications follow. No continuous energy loss. Motion does not require maintaining curvature deformation. Uniform behavior. Across scales, the same 2.1 ratio governs planetary and galactic systems. Stable background structure. The underlying propagation stage remains constant. Only pressure and motion vary. In general relativity, Einstein doesn't have a single little g equation like Newton's F is mg. Instead, he replaced the idea of a gravitational force with the Einstein field equations, Fe, which describe how the 3D grid of space-time curves. However, to find the equivalent of the 9.8 short-text for MS2 we experience on Earth, you look at two specific areas of his work. 1. The geodesic equation, how things fall. The equation for g in Einstein's terms is actually the geodesic equation. It describes the acceleration of an object as it follows the curvature of the grid, and gamma, Christoffel symbols. These represent the gravitational field, or the tension warping of the grid. On Earth, the result of this equation for a falling object is exactly 9.8 text n2. Einstein viewed this not as the Earth pulling the object down, but as the object following its natural straightest path through a warped grid. 2. The Einstein field equations, what creates G. To determine why the grid is warped enough to create that 9.8 wide text ms2 acceleration, he used Einstein's equivalence principle. Einstein's most famous insight regarding G was that gravity is indistinguishable from acceleration. If you were in a windowless room in deep space, 0G, and the room accelerated upward at 9.8 high text ms2, you would feel exactly like you were standing on Earth. In your model of a pressurized medium, Einstein's G is essentially the pressure gradient of the grid near a massive node, Earth. The 9.8 high text ms2 is simply the rate at which an object slips or glides toward the center of that pressure warp. Does this mathematical view of the warp change how you calculate the 2.1 ratio for space expansion in your kinetic grid model? The quantum physics geodesic gravitational theory proposes an alternative interpretation of gravity and cosmic motion, unifying local planetary behavior and large-scale cosmology through a structured propagation framework. 1. Dual nature of gravity. In this model, gravity consists of two components. Geodesic space, local gravity, governs planetary scale motion, producing the observed acceleration. 0-point space field global propagation defines the underlying structure through which all motion occurs, setting the universal propagation limit at the speed of light, c. The relatively small value of 9.8 ms compared to 18.6 ms is attributed to local density conditions. Earth's mass creates a specific pressure gradient, establishing a stable equilibrium rate of propagation. In contrast, c represents the maximum propagation limit of the system. 2. Propagation mechanics. Propagation occurs through discrete structural elements, nodes, that transmit motion. At low acceleration, e.g., propagation is smooth and stable. As velocity increases, nodes must transition states more rapidly. At CE, the system reaches its maximum refresh rate, beyond which no further propagation is possible. Thus, gravity can be interpreted as a low-speed manifestation of the same mechanism that governs light speed limits. 3. From curvature to pressure. While general relativity describes gravity as space-time curvature, gravity wells, this model replaces curvature with expanse pressure. Instead of objects falling into wells, motion is governed by a pressure-driven propagation field. This leads to a reinterpretation of orbital mechanics. Planets do not orbit due to falling into curvature. They follow stable paths determined by a 2.1 expansion ratio, forming a mechanical constraint, or track. This shifts the framework from geometric distortion to dynamic flow behavior.